A very important part of concrete mix design is understanding the hydration process of cement, and this is what I will try to explain in this video. So a brief outline of what I will be going through in this video. The hydration process of cement is the first topic that I'll be talking about, and then we'll move on to flash set. I'll describe what flash set is, and I'll describe how this can be avoided during the setting process of your concrete. Let's start by looking at a quick overview of the hydration process. Hydration, as you are aware, it's a chemical reaction. So it involves dissolution and precipitation. In dissolution, the cement grain dissolves, and when it dissolves, it starts reacting with the water, and then that's when precipitation takes place. It's because hydrates are being formed. It's usually a very long process, so you can't think of it as taking days. Even though your concrete does set and it achieves required strength within typically 28 days. However, the hydration process itself will continue on for years. So you can, think of it as like maybe taking about 10 to 50 years to achieve close to full hydration. You never achieve full hydration. Hydration is important as a chemical process because if we understand hydration, we can understand the process that concrete undergoes when it sets, and that allows us to control that process of setting of the concrete. Hence you can transport concrete to construction sites that are located very far away, for example. In terms of the process itself of hydration, we can summarize it through the figure that you can see in front of you. So there are 5 main stages associated with hydration. Stage number 1, so you can see there's a massive peak in the rate of change of the heat that evolves from the mix, and this usually happens when you add water to your mix. Stage number 2 is the dormant period, and that's why you see a massive drop in the rate of heat that's released. The dormant period is important for transportation. That's when the hydration process is at its lowest, and hence you can transport the concrete before it sets, so it's still malleable. The 3rd stage is the initial setting period. The 4th stage is sort of the final setting period. And then finally you have this stage that's associated with very low levels of hydration. Now, the products or the constituents of cement, as we said, there's 4 main constituents. That's C3S, C2S, C3A, and C4AF. And the process of hydration for each one of them, roughly speaking, it follows the graph that you can see in front of you. But usually what takes place is that the hydration of C3S would occur just a bit before, or be finalized just a bit before C3A. C3A, of course, is the one that has the greatest rate of hydration. That's why we add gypsum to our cement when we produce our cement product, to make sure that we control that hydration process. Now, as I said, the 4 main components of cement, they all hydrate at the same time, so it's a simultaneous reaction that takes place. However, there is a difference in terms of the hydration rate. So these different constituents, they have different hydration rates. Generally speaking, however, in order to increase the rate of a reaction, you have to make sure that the grain sizes are very small, and that's just from chemistry. So the smaller the grain sizes, the bigger the overall surface area, and the easier it is for the reaction to take place. So that's why we need to grind the cement in the cement production process, and this is a process that I've talked about in a previous video. So looking at the degree of hydration for these 4 main constituents of cement, what you notice in the graph is on the y-axis we have the percentage degree of hydration, and then we have time on the x-axis. The highest degree of hydration is associated with C3A. Now when you add gypsum to C3A, it lowers down a bit. You can see that in that second graph. So there's C3A plus the gypsum. And then the 3rd highest degree of hydration is associated with C3S, and C2S is the one that's associated with the lowest degree of hydration. Now, these different constituents of cement, they have different products that are produced during the hydration process. Let's start by looking at the calcium silicates, so C3S and C2S. What are the products of the hydration process for C3S and C2S? Well, when the calcium silicates, when they react with water, what results is CSH, that's just shorthand notation for calcium silicates hydrates, and then you have your calcium hydroxide, CH, also referred to as Portlandite. The CSH is the main cement hydrate in Portland cement, and it's the component that provides the major strength requirements that are needed in your concrete mix. CH, on the other hand, it does contribute significantly to strength, and it does so through reducing the permeability of the overall mix, and this is due to its morphology. So if you compare the morphology of CSH to CH, you find that CSH is more like a gel product that is cohesive in nature, and that's why it contributes to the major strength, whereas CH is more of hexagonal shaped structure, and the hexagons can sort of interlock with one another, and hence that's why it reduces the permeability of the overall mix. When we look at the calcium aluminates, the hydration process results in different products. For the hydration of C3A, there are two main products that we now look at. So it's ettringite, which is the first hydrate that's produced, and then monosulfur aluminate, and that's produced after the ettringite is produced. So in order to produce monosulfur aluminate, you need to have ettringite present, and then the ettringite reacts, and the final product that results from the hydration of C3A is monosulfur aluminate. Now, ettringite has almost no contribution to long-term strength. On the other hand, monosulfur aluminate does contribute. However, the contribution is way lower compared to the hydrates of C3S and C2S. For monosulfur aluminate to be produced, the ettringite reacts with the sulfate in the mix, and that leads to an internal expansion in the concrete. Now, this is a very important point to discuss, and that's flash set. Now, flash set, the importance of studying C3A, as you've seen, there's no major contributions to strength. However, what C3A does is that it controls the setting of the concrete. So if you control its hydration rate, you control the setting of the concrete, and this is very important, for instance, when you're transporting your concrete to construction sites that are located very far away. So the C3A reacts with water, and the reaction is very rapid without gypsum. And that's why if we were to have a cement that excludes gypsum, then we'll get a lot of issues when it comes to setting time. We'll have immediate setting of the concrete, and it's no longer as malleable as we require it to be. And that's why we add gypsum in the cement production process. So gypsum plus C3A, it delays not only the hydration of C3A, but also delays the hydration of C2S and C3S. And that's how we get our dormant period in the hydration process.